recording now,
Great.
and then I'll send you a link to the recording. Okay.
Nice, nice. You are prepared, sir.
Well, I'm on Zoom every day, so we're. Normally, I have the virtual background on, but it doesn't show stuff that I want to show
Right.
you nicely. So you have to put up with my mess behind me.
Oh, no, no worries. I actually broke away from the kids, so I'm trying to isolate my 1 hour to myself, fully devoted to this. I'm looking forward to this.
Okay, so what I'll do is I'll start off basic, but if there's stuff that you're already familiar with, just say, hey, I got this. Move on. Okay.
Okay, just to
Uh,
let you know, I spent the past, say, 20 minutes doing a YouTube crash course, and it kind of walked me through all the basics. But that's just really to get me re-familiarized with the software. But by all means, let's start from the top, and you know,
okay. Now I'm using a Mac here. The interface is just a little different
okay,
on those, but the functions are all the same.
great.
The menu may look a little different. So let me just okay. So this is of course where you start, right? You got nothing here, and you're looking. Where do I start?
Okay, I'm
And
gonna I'm gonna I'm gonna open a fresh screen. Got it. Okay, good.
okay, I'm sharing a screen with you. Do you
I
see
see
it?
that. Yep, I see that.
Okay, good. All right. So basically, there's three things that you tend to do in sequence: rocket design, picking your motor, and then doing the flight simulations. Okay.
Got it.
Now, truth be told, most rocketeers don't do a whole lot of rocket design because their kits that they buy come with the Open Rocket or RockSim file to begin with. But
Right.
I'll show you how to build one from scratch. Okay,
Okay.
because you're going to need to do that for Tark.
Yep.
Um, and I'll also tell you that while I use Open Rocket a lot, and I'm a level 3 flyer, I probably only use 2/3 of its capabilities. Because that's all. There's a lot of other stuff here that the other 1% will use.
Okay.
Okay. Now, one thing Open Rocket has um, are some example files,
Nice.
right?
Okay.
So I'm going to file. I'm going to open up the simplest model rocket right here. Whoops! What happened to it? Do you still see it?
I do not. Oh, something just popped up.
There we go. Okay. Do you see it now?
I see us.
Oh, you see us? Okay. Somehow I lost the share. Let me go back. 1 second. Click. Click. Of course, my uh, 1 second. I'm just going to stop the video and figure out what's going on here. Share screen. Again, I'm just going to share my desktop in its entirety.
I see it.
Now you see my desktop, and we'll go back to Rocket. Okay, there we go.
Yes, I see it. Yep, I got the same thing.
Okay, so this looks like the probably the alpha or the type of rocket that you were building with the kids from the
Right.
SD kit, right? Very simple: nose cone, body tube, 3 fins. This, a small Estes motor
Yep.
and a lunch log here.
Wow. Yeah. Very
Okay,
accurate. Very accurately modeled. Yep.
okay.
Got it.
The other things that are in here are um, the shock cord
Yep.
and parachute and even the wadding.
Oh, okay.
Okay, and I wanted to show you this first before we build our own. Okay,
Okay. Good idea.
because this is the very basic model. So you have a nose cone. I'm just going to click on nose cone here, and this window comes up and describes the type of nose cones. Most nose cones are going to be the ogive.
Ogive. Yep.
Okay, but there's others. And if I wanted to change it, I could change the nose cone to different shapes and styles. But ogive tends to be the one that most rockets are going to have.
Okay.
You see, this has a length of just under 4 inches
Mm-hmm.
and a base of just under an inch. Okay, so a small rocket, This is known when people, when you're looking for nose cones, this is a 4-to-1 ratio,
Okay.
which is diameter to nose cone length. So if someone says, hey, there's an ogive nose cone that's 4-to-1 or 5-to-1 or 6-to-1, it's all in relationship diameter to length.
Right.
Okay. And there's different components. We'll go through these others, as we go.
Got it.
Okay, but and it tells you what the mass of this component should be given the material.
Got it.
See, it says 13.2 grams, and I would very recommend for weight and measurement. Well, most of my measurements are done in inches, except some I do in millimeters, and I'll show you why. But grams, because Tark will tell you the rocket can be whatever 600 grams. So instead of having everyone constantly, do the math back and forth, you can just set the thing to grams. Okay.
Got it.
And by the way, where you do that,
Edit preference, correct?
in the preferences, right?
Got it.
I go to preferences under units. I can set all the different things to the different units.
Okay.
So see, I have dimensions in inches, motor dimensions in millimeters, because that's how they are sold.
Right.
And I see I have mass in grams here.
Got it. And I just changed mine to match yours.
Okay. All right. So you have the nose cone. In this case, now I have a body tube, which is this part here.
Mm-hmm.
And what's below what's indented from the body tube are all the things that are included with that particular body tube.
Got it.
So there's fins, there's an inner tube, which I'll describe, engine block, centering ring, shock cord, parachute, wadding, launch loop. All those are attached in some way to the body tube.
Got it. Yep.
All right, so this body tube is, for whatever reason, just short of 12 inches.
Okay.
This one just happens to come with, so I don't know, so it's a 12-inch. This is probably normally a 12-inch body tube, and it's 1 inch in diameter, made of cardboard, and should be 15 grams. I'll do the fins last.
Okay.
Inside here is another tube that the engine fits into, and that's known as the inner tube.
Ah.
And that's why I brought some show and tell.
You are off camera right now.
I know. I'm going to go back in camera.
Oh, got it. Okay.
Give me 1 sec, and I'll get back on camera. And I'll give you a little show and tell. All right.
I see it.
Wow. It's a very big rocket. All right. You see that tube in the middle?
Yep.
So that's where the engine goes in this rocket.
Got it.
It's very, this is just a bigger, this is a 4-inch rocket. That's a 1-inch rocket, so it's a lot bigger. But that tube fits in the middle of the outer tube, and that is where the motor goes. And in your Tark rocket, you're going to have the outer booster tube and an inner tube just like this. That inner tube is connected to the outer tube with these things here. These are called centering rings.
Got it.
See, and what they look like in real life is this.
Mm-hmm.
So here's one I'm going to be putting together from scratch. These would go in here.
Mm.
Once I sand them off, one would go in there, and then the tube would go in the middle.
Got it.
This is for a 38 millimeter motor in a 4-inch. Okay.
Got it.
But whether you're building a Estes rocket like this or a 10-foot rocket, they all have these centering rings with the motor tube.
Got it. Okay.
And that's why you see these things that are called centering rings here. And I'll show you how to make them, but that's what those are. Okay?
Got it.
Your shock cord, you just put in a shock cord and you determine what it's made out of.
Mm-hmm.
Maybe at the end I'll give you some hints on what to make it out of.
Great.
But let's say it's this, and let's say I wanted to make it 3 feet instead of that. I make it like that, and this just moves where it would be packed. You see it moving up and down in the rocket there. All right, it's just adding a weight component for the shock cord and trying to determine where you would put it.
Got it.
You're going to put it up to the top probably because here's the wadding here. If I move the wadding down here, I would move the parachute down, and why that matters is this symbol here is the center of gravity.
Mm-hmm.
This symbol here is the center of pressure of the rocket.
Got it.
This thing, stability over here, is very important. That tells you, you always want that greater than 1.
Yep.
If it gets too high, what's too high? Ask 10 Rocketeers, you'll get 20 different opinions. But the higher the stability number gets, the more it will what's called weathercock. That means fly into the wind, being overstable. Rockets always fly into the wind under power, and then obviously the parachute will have a drift back. That's because the bottom of the rocket is like a big sail,
mm-hmm.
and it will, turn it into the wind because the wind is hitting, there's more force in the bottom, and it always flies into the wind.
Got it.
The higher this number is, the more the propensity for the rocket to fly into the wind, because that means the center of gravity is even higher up.
Got it.
So the pendulum effect is even more. Just something like you wouldn't want to set up a rocket with a stability of like 6. That
right.
Would just, any little puff of wind and it's going to go, that way. Okay.
Got it.
The launch log. So these are all the components. We're going to put the same components into a sample TARC rocket in a second. Now the fins, I said, are last, and they have some standard fins up here, the trapezoidal, the elliptical, or you can actually draw one through freeform here. These are the fin templates up here.
Got it.
You're probably not going to use tube fins. Are just tubes on the side of the rocket that act like fins. It's actually a very cool design. My wife loves making them. So the rocket just has tubes that funnel the wind, and it acts as, but you're not going to be using that. You'll be using most likely the trapezoidal or get more sophisticated, the freeform. So this is trapezoidal, and when you put it on, typically your TARC rocket will have 3 fins. There's no additional stability you get from 4 fins versus 3.
Mm.
And all you're getting is a little more weight.
Okay.
So unless you're really underweight for some reason, and there's also other places you can add weight to a TARC rocket. Normally it would be 3 fins.
Got it.
Okay. Now, root cord on your fin. Just watch what happens to the fin when I just click this. The root cord is how far it goes up on the rocket. It's this length.
Mm-hmm.
That's root cord.
Okay.
Tip cord is this, so I can See, that's making this length longer.
Okay.
Okay. Height. Well, that's the height from here
From the body. Got it.
in the body. So this goes like that. Pretty straightforward. Sweep length is this length right here. And you'll find that these become like this is a very standard shape. I'm not, unless they're designing their own fins, they'll probably purchase something that or copy something that is very standard. Okay. Now, the other thing you should know that's a difference between a whoops, go back. A small Estes rocket like this and a Tark rocket is a Tark rocket. An Estes rocket, you're gluing the fin right on the body tube here.
Mm-hmm.
Right. In a Tark rocket, you're going to do something called through the wall attachment, and what that means is more likely than not, you'll purchase a body tube that has slots already cut right where the fins should go.
Right.
And the other thing to show in my show and tell here, let's see if I can get that closer. Oh, you see that how the fin goes like through the wall there?
Let me see. Yes, I do. And it connects to the inner tube. Is that right?
Connects to
I
the
see
unit.
that.
Yeah.
Yep, I see it.
Right. That's why. So that gives a tremendous amount of strength to the fin attachment.
Right.
So I'll show you that in a second. But that's another difference. Now here, the last thing I'll show you this, and then we'll go to the Tark example. Is when I go to motors. These are probably motors that are familiar to the kids. I don't know whether you use the B44 or A83 or any of these. But these are just configurations that they put in here. If I wanted to create another configuration, let's go to new configuration. I would select a motor. I probably want an Estes motor. Let's say, and these are the impulses. And let's say you're choosing an A or B. And let's say I want a B6 motor. And the ejection charge is 6 seconds. Let's say it's a B66. I don't know, I did B60. Let me fix that. B6, maybe it's B64. Okay, here's a B64. I go to flight simulations. It tells me my B64 with this rocket will fly to 468 feet. It tells me that the apogee is at 5.2 seconds. This is going to become very important with Tark. So with a 6-second delay, a 4-second delay, I am actually popping the parachute before it reaches apogee, which means I am, see, here's the 4-second delay here.
Yeah.
It's telling me what the optimal delay would have been. And it tells me how long it's going to take to get to apogee.
Okay.
So, 4 to 4.6, that's really not that bad. You're not going to get much closer than that. And then it tells me what the total flight time is. This is something else that becomes important for Tark, because you need a 43-second or 42-second flight time. Okay. And it tells me with that size parachute how hard I'm hitting the ground. Okay. And you can see there's a bunch of different motors here that have different characteristics.
Okay, so I kind of slightly lost you here, Stephen,
Okay,
at the motor selection. So you went to the motors and configuration tab.
so I went here. I'll go slow,
Yeah. And
and
over here,
I clicked new configuration.
oh, I see. Okay.
Now it says no motors. Then I went here and clicked
Oh, you gotta select the motor.
select
Got
mode.
it. Oh, I
Okay,
see it. Okay. Got
and
it.
and these are all the different manufacturers of motors.
Okay. There's a lot more than I ever thought.
I'll show you the two you're going to need for Tark. They're going to be Cicerone and Apogee.
Got it.
Uh, but since this is a small Estes rocket like you're familiar with, I just picked Estes, and I just happened to, you could pick, if I wanted to pick a larger Estes, I could move this up to C and give me
Oh, I
C
see.
impulse,
Got it.
the the okay, and it tells me what the diameter of the motor is here. These are 18 millimeter, and I happen to know this is an 18 millimeter motor case, so that's
Got
what I'm
it.
for. Um, and it also tells me what the length of the motor is. You see the motor is sticking out of the end here a little bit,
Yes.
or will be. Anyway, so that's how you do that.
Got it.
All right. Um, when I get to the more sophisticated stuff, I can show you recovery, and you're not doing staging, so you don't need to worry about that.
Okay.
So this is all the modeling you could do on the existing Estes rockets that you guys have, or flew last year, I guess. Right?
Yeah.
Um, there's a good chance that if you Google the particular Estes rocket that you have, you might find an open rocket file already made for it.
Nice. Okay.
Right? Um, those rockets have a extension on the end that's .ork. Okay.
Got it.
There's another program that's compatible with OpenRocket, sort of, that's called RockSim.
I've heard of it. Yep.
So RockSim is a for pay program from a company called Apogee Rocketry. If there's a RockSim file, you can use it in OpenRocket.
Okay.
Okay.
Got it.
So, like I said, if anyone wants to get just before you have built or designed the Tark rocket and want to get proficient with OpenRocket with their existing Estes rockets, you can do that.
Got it.
Okay. Now, while I'm still talking about the Estes rockets, you see here, let me go back. Let me take out the motors. No motors. You see, it says the mass without any motors is 46.7 grams.
Yes.
Okay. I will guarantee that when you build it, it won't be that.
Mass with no motors. Right.
Right? The reason it won't be that is maybe someone was a little heavier on the paint, heavier on the glue, whatever. It's So what you would want to do is, when you actually have a physical rocket like this, obviously weigh it before to compare it to what OpenRocket is saying it is. Okay.
Mm-hmm.
And you would weigh each separable component. Well, in this rocket, there's only two separable components. There's a nose cone, and then there's a body tube with everything connected to it. If you recall, we go back to the rocket design, there's a nose cone and a body tube.
Right.
So let's say you weigh the nose cone, and you say, hey, my nose cone is 20 grams, not 13.2 grams. It says it's only 13.2.
Mm-hmm.
You go to override here,
Nice. Okay, I get it. And
and
you
I
start.
and I just override the mass to 20 grams.
Okay.
You don't have to worry unless there's some specific weighting that you're doing with the center of gravity. Normally, I just leave that alone. And now it's 20 grams there. Okay, now the rocket's 53.6 grams.
So
Okay.
would you consider this to be part of the calibration process?
Absolutely, yes.
Okay, got it.
Okay.
So the
But
override.
you can't do that until you've actually built the rocket for the first time, right?
Right.
And what you'll find is, let's say they build 4 Tark rockets, 5 Tark rockets. Each one
It's gonna be slightly
will,
different.
will be a little different. I mean, even the master builders will have it slightly different for whatever reasons.
Sure.
Okay. Um, Normally, if you're doing what I call sport rocketry and you're just going out to have fun with it, it doesn't matter a whole lot.
Hmm.
But if you're doing Tark, grams matter.
Right.
So that would be part of the calibration process is getting the weight. And within the body tube, for example, these fins have a particular weight associated with them, 4.52 grams. Now, they happen to say these are made out of cardboard in this particular case.
Right.
If they're made out of something else, I could just click this and find another material that they're made out of. Okay?
Yep.
If you don't find something that's close, you can click custom and make up your own thing here.
Hmm.
Jersey City special. Okay.
Landfill.
Whatever. Okay, yeah. And then you just add it, and then from then on, it's in the database of Jersey City's.
Nice.
Okay. Um, you're probably going to be using something that's close to maple or some pine, maybe. Is probably pretty close to what you would use in a Tark rocket.
Okay.
But if the mass is off, again, you can go to override and just override the mass and put in what it really is.
Got it.
Okay. So at the end, the open rocket mass with no motors should be a very close calibration to your actual physical rocket.
Got it.
A lot of people miss that part. Okay.
Okay.
Um, it's just part of calibrating the model. Okay.
Got it.
All right. Should we,
Now, can I ask you something else? So in
sure.
the override and in the calibration, obviously, ideally, you would want to calibrate almost each and every subcomponent as well.
Yes, you would.
Yeah, because this would.
So I would take the parachute out and weigh it
Yes.
before I put in before I attach the shock cord. I would weigh it.
Right.
Yes, the more you can weigh each and every component, on a good scale ahead of time, the better. Then you could, because like for example, the parachute has a mass to it.
Right.
I could override that if that's 10 grams instead of 8 or whatever.
And then equally important would be the actual distances of each component, because that might affect the CG, correct?
Oh yeah, oh absolutely. You see, if
Yeah.
and that's why repeatability becomes very important. So
So,
wherever you pack the rocket,
right.
and once they have that dialed in, normally there's someone on the team who's the packer.
Mhm. Oh, wow. Okay.
Okay, I mean there's all these different roles that you can have on a team for
Yeah.
consistency. There's someone on a Tark team whose specialty becomes packing the egg.
Mm.
Right? And why? Because they do it the same way each time. If you have 5 kids doing it, it'll be different every time.
Mm.
And
Okay.
and since Tark is an engineering process, you want to limit the variability so that when you're trying new things, you're only vary. Suppose you're you're flying your Tark rocket and you fly it on a particular type of motor, and you say, hey, let's try this other motor. That's the only thing you want different.
Right.
Between those two flights. You don't want someone packing the parachute and putting it at the bottom versus the top, or
Got it.
packing the egg different, because
So
all of that impacts the result.
limit the variability. Got it.
So ideally, you just want on any test run to have one variable that you're testing for and keeping everything else constant. Otherwise, you're doing multivariate analysis and forget it.
Right. Right.
You don't know what affected what.
Too many moving targets. Got it.
Too many moving parts, right?
Yep.
Exactly. Okay.
Got it. Yep.
All right. So, should we try and build one from
Sure.
scratch? All right.
Sure.
So I wanted to give you this first because this is a rocket, obviously you're familiar with,
Mm-hmm.
and so let's start something new. Okay.
All right.
All right. So now we're flying without a
Flying into new
Flying-
skies here, new territory. Got it.
territory. All right. Let's so right now it's just a blank slate. So I like to start at the top. So we'll just pick a nose cone.
Got it.
And let's say we're building a Tark rocket. Probably is 2 inches across. If it's going to fit an egg, that's 1.7 inches. So I'm going to make I'm going to go up one. I'm going to make so the base diameter here is a little less than. The reason these aren't quite 6 and 2 is there's some thickness in the wall of the cardboard.
Yep.
You could take, if you actually want to test it, you just take a caliper and measure the width of the cardboard. But all right, so but the nose cone's not going to be made out of cardboard like it says here.
Mm.
So let's pick something else. Let's say it's a plastic nose cone.
Okay.
Plastic. Here we go.
Got it.
Okay. This is a 3-to-1 ogive nose cone, and you see it goes from 0 to 6 inches on the scale here, right? You see the ruler on the top.
Oh, I see. Okay.
Yeah, and that's 6 inches. We could even make it a little bigger so we can see it. There we go, 6 inches. Okay. And this component finish, leave at regular paint to begin with, but this is a very interesting thing to use to calibrate as one of the last steps.
Okay.
Okay, and let's say I've bought my nose cone, I have it. I would weigh it, see how close it is to 25. But let's just assume that these weights are correct. Okay.
So just before you leave on this one, I could not find plastic on my list, and that seems to be the only thing different.
All right. So if you don't have plastic, what you could do is go to custom and make it.
Ah, okay, got it.
And plastic is 0.85 grams per cubic centimeter. I probably put that in as a that might have been a custom one for me.
0.85, got it.
Okay.
Interesting. Good. Okay.
Right. Sometimes they're polystyrene. These other most of the real stuff is fiberglass, but you're not going to be using that. Okay.
Now, okay, so far so good, but you're back on cardboard. That's why.
Yeah, I'm going to put back the plastic.
I just want to see if our masses match approximately. 25.5. Good. I got it. Okay, I'm with you.
All right. Plastic. What happened here? I don't know what this little antenna thing that I
Yeah, I
somehow.
got that earlier. I think
Let me.
there's
Because I
two
have
nose cones. Yeah.
two skills. Let me delete one. Okay, there we go. Okay.
Yep.
Now, as I build the rocket, I mean, it's always going to tell me where the center of pressure and center of gravity is. Obviously, it doesn't matter much, but I'm just have a nose cone here.
Right.
Um, but as an example, you see where it says the stability is negative?
Yes.
Yeah. Um, and you always want that to be at least +1. And negative stability will tumble right off the. Okay.
Got it.
So next we want a body tube.
Yes.
So I'm going to click body tube. Whoop, I got two body tubes. But sometimes actually you want two body tubes for Tark, so I'm going to leave the two here, and we'll make one of them a payload for the egg.
Got it.
All right, so I have this. I'm going to call this body tube 1, and I'm going to call this body tube, and this is where we're going to put the egg in this particular example.
Body tube egg. Got it.
I just created a name for it. Okay.
Yep. I'm with you.
Um, Now the only thing I'm going to put here is a parachute and some stuff. So let's say I'm just sort of, you see, this is body tube 1 is 8 inches. Maybe I'll just make it 6 inches,
Okay.
just for kicks. Yeah. And it's cardboard and it's 31 grams, and I'm up to 100, a little less than 100 grams for the whole rocket.
I'm with you too. Yep.
You with me? Okay, good. Now I have the body tube for the egg. And that, let's say I'm going to make that 4 inches because I want it to be tighter for the egg. Okay.
Got it.
Now, there needs to be a, let's see here. There needs to be some sort of bulk plate here because otherwise the egg would jump up here.
Mm-hmm.
So in here, see what it says bulkhead?
Yep.
So I'm going to put a bulkhead. Now I happen to put it at the bottom. And let's say my bulkhead is made out of pine. And you see what it says bottom of parent component? I really want
Yes.
at the top of the parent component.
Got it.
Whoop, top. And now I'm just going to see how by sliding this, I'm moving up this bulkhead up to here.
So, okay.
Relative to the top of parent component, I made it 0. So it's.
Oh, I get it. Okay, got it.
Now you see how this bulkhead, you can see this doesn't quite go all the way to the body tube.
Mm-hmm.
So I can make it do that. Now this is where I use millimeters, because millimeters are the smallest component.
Mm-hmm.
See, I just changed from inches to millimeters. I just go up a little, and I'm just watching it, and then okay, that's good enough. So that is a bulkhead here,
Got it.
and we're gonna have another bulkhead right here because this is where the egg is gonna go.
Got it.
Mm-hmm. So I go back to this body tube. I'm going to add another bulkhead. And now it's at the bottom. That's good. By the way, there's no guarantee that this is an optimal Tark design. This is just
Yeah.
for demonstration purposes only.
Got it.
All right, now, again, I'm going to change this to millimeters because it's easier to make. And then I just extend that. Okay, good. So now I have some payload here. I have a bulkheaded area here where I can put something. And now I'm going to have the rest of the rocket over here with the fins and the motor. And okay. As I'm doing this, I'm realizing that this is going to be too long because the parachute's going to be in this section. So this will be, let's just make this 4 inches. All right, so I have two. I need some place where I'm going to put the altimeter.
Right.
Right. And you have to have it. So let me just theoretically say I have a little section up here for an altimeter. One thing I didn't do on the nose cone, let me show you, is something called shoulder. The nose cone has to, it doesn't just sit on top of it.
Right. Insert into it.
Right. So there's a shoulder. And I want this millimeters. So that's the shoulder, and now I'll just make it. There we go. Okay. So now the nose cone fits in to this part.
So the diameter, was that just something you kind of estimated from?
Yeah, I just did it by eye, but you could actually, in theory, you would know what this is. I'm just looking at this line from here to here, and might be off by a millimeter. There we go.
Oh, I see what you're saying. Okay.
I just did that by eye.
Got it.
Okay. All right. So I have the nose cone. It's sort of fitting into this section, and then I have this other section, and I have some bulkheads here. Okay.
Got it.
Now I'm going to add one more body tube, which is this. And I think a Torque rocket has to be at least 24 inches. I should have looked at this year's thing, but let's just say it's that. Okay, so I'll make it 12 inches.
And I guess you kind of did that by eye just to like balance out the final length to be.
Yeah, because I'm looking at this is 25 inches.
Got it.
So, if if I'm just if I say the Torque rocket has to be at least 24 inches, we'll see. A lot of Torque rockets will be 3 feet or something. So there's not. I'm just giving you something that's at least 2 feet long as an example. But you could just make the body tube as long as you want by just keep on going.
Yeah.
All right.
Okay.
We'll leave it at 14 inches like that. Okay. Now, let's remember a few things. Well, what we have to put in, we have to put an inner tube that's going to host the motor with those rings that we talked about earlier, right? These things. Right? And then we'll put some fins on it. Okay. Now, a Torque motor typically is 24 millimeters. And they're typically F, in the power range of the F motor.
Okay.
Okay. Now and we'll put some motors in here to show you that, but let's say it's F. I think most Torque teams that I've seen, have an F motor.
I haven't even graduated from a C size yet, but that sounds.
So, as you know, the power doubles each letter. So D is twice what C is, and E is twice what D is. And
wow.
F, so you're going up. you're dealing with what is usually called a mid-power rocket.
Okay.
Okay. Um, but they're 24 millimeter typically. All right.
Got it.
So I'm going to click this body tube, and you see this thing that says inner tube right here. Inner component, inner tube.
See it?
Okay, I'm just going to click that, and I'm going to go to millimeters here to help me out. So I know the inner diameter has got to be oh yeah, I gotta get the outer diameter to 24 inches. Let's say 25. And so let's say it's a 1 millimeter tube, and the tube usually they're 6 or 7 inches. Let's say this one's 7 inches. So there's a tube. This red thing here, and this is what the motor is going to be put into. Okay.
Okay.
And cardboard is usually what these are made out of, so that's good. All right. Now I want.
Cardboard. Got it. Yep.
Okay. Now, to hold the tube in place, I need some centering rings. And here's the centering rings here.
Okay. Wait. I fell off the wagon. The length of your inner tube was 7 inches, correct?
7 inches, right?
Oh, there it goes. Okay.
I just picked that. I mean.
No, I just want to match yours. Yep. I got it.
Yep.
Okay, I'm with you. Yep. I'm
Right,
coming in about 10 grams higher than you, but that's okay. I don't know where I went off there, but that's okay.
Well, we can check that after, okay?
Yeah, okay.
Here's a centering ring.
Got it.
I'm going to take a centering ring. Centering rings are not cardboard. They're usually of some wood. Let me just pick pine as an example.
Okay.
And you see where the centering ring, they put it right here.
Yep.
I'm going to leave one. Usually you have one at the bottom. Like that. And I'm going to put one up toward the top. Some people put 3 rings, but you got, see, I'm dragging the position relative, and normally I put the ring, let's say right there.
Okay.
And now I'm going to do this by eye again. But, okay. Now I'm going to do something here to the inner tube. This will, I'm going to move the inner tube a little beyond the bottom of the rocket. Okay. And there's going to be a couple of reasons for that. One is it won't burn up your rocket.
I see.
But if you remember on your Estes rockets, you probably had like a little clip here to hold on.
Yes.
Well, a little clip is not going to work on a big motor like this. So there are different types of motor retention devices that you can put on here. Some are just almost like a piece of metal that's tied to a screw that sort of slides over this thing and then ties down. There's you could look up on YouTube, and if you get stuck, I can help you. But trust me, you need some motor retention here. Okay. The reason you want this besides for the fact that it won't burn up your rocket, is when your rocket hits the ground, the strongest part of the rocket is going to be the motor casing that's in here. And if it hits this first, it'll do less damage to the rocket when it hits the ground.
Okay.
Right? Trust me on that one.
I can picture it. So wouldn't that be the nature of the where the parachute is tied and you would want the rocket to go?
Well, um, yes. And like I said, a lot depends on where you tie, where you tie the parachute.
Okay.
If I'm tied, like the way I've set it up here, the parachute's actually going to be in the middle,
Hmm.
and these two pieces will fall like a V.
Right.
Um, some people tie the parachute up here, and the thing falls in a straight line.
Right.
Um, you know, and that's part of the learning process is to try it out in different places. I'm just giving you one example here. Um,
Okay.
but the other thing is now when we put the fins, we don't want the fins to extend off the back of the rocket. You don't want a fin that comes like out here.
Okay.
Because as the rocket comes down, the worst thing that could happen is it hits the tip of one fin,
Yep.
because that will create a lot of torque and force on that one, and you'll break your fins.
Got it.
Um, so typically you'll have your fins just maybe a quarter inch or so off the bottom, and we'll put some fins on now, but that's where you'd want it um, for survivability purposes.
Okay.
If you see like these, I don't know if you can see, but they're off the bottom of the rocket. You see,
Got it.
I mean, this rocket has has gone past its flyby days, so I cut it and I use it for things like this just to show people. But that's why this doesn't go all the way down, and these sort of go back. So if this falls, when it falls, it would hit the motor mount and is not likely to hit a fin
Right.
directly. Or at least that's the idea. Okay.
Nice.
All
Okay.
right. Let's put some. So what's next? Fins. So I'm gonna go to trapezoidal fins. Ready? Let me know.
Yep.
All
I'm
right.
ready.
All right. So when I click trapezoidal fin set, it automatically puts 3 fins on there. Okay. Now you see how these go. See where these are? They go all the way to the bottom and they can't off.
Yep.
That's not a fin. I mean, that may look cool, but you're going to be doing a lot of repairing the fins.
Right.
Right. And you see, as soon as I put the fins on, now the center of pressure is a little behind the center of gravity.
Oh, okay. Yep.
But I know I'm going to have some weight up here.
The A. Yeah.
So I need to move. So this is going to, move further up. So, um, this might not be a bad size fin for this rocket. But I'm going to do a couple things. I'm going to increase that like that. And I want to move this up the frame just a little bit, just to give you my example. You see, I just moved the fins up from the bottom.
Yes.
Now, in reality, if you buy, most likely you'll buy these body tubes from someone like Apogee.
Hmm.
And when you do, and I'll show you how to do the through the wall tabs here. Where the cut will be up from the bottom for this reason. You could buy your own tubes and cut them yourself, or you can buy pre-cut tubes.
Okay.
Right? And let's say this is not cardboard. This again, let's make this pine. The thickness, this is a 1/4 inch. That's about right. I haven't talked about fillets yet. We'll do that last. Fin tabs.
Hmm.
Now I'm going to do this by eye again, but I'm just going to, I'm growing a fin tab at the bottom of the rocket here, and I want it to touch the red
Oh, I see.
like that. And I know the length. Let's say I make the fin tab the entire length of the fin. Okay, so now these go through a cut here, and they're going to attach in. And I'll give you some hints on how to actually attach that real well. But so now I have a couple of now I'm almost ready to fly this thing. Now I have to put in a parachute and a few other things. So let's get that. So let's say the parachute I'm going to put here because the ejection charge is going to come out of this thing. And let's see here. This is not quite right. I need to. All right. If I was doing this really correctly, this would sort of. This has to be like a little coupler here.
Mm-hmm.
Right now, they're just sitting on top of each other.
Yep.
You see, I realize that this ejection charge, there's nothing connecting
Got it.
this to these two body tubes. So
Got it.
let me put in a coupler. Yep. Outer. I want the outer diameter. 1 sec. It's a little too.
Do I also need the bulkhead still?
Yeah, the bulkhead should move to the either side of the coupler,
Oh, I see. Okay.
and we'll move them. Oh, that's wrong bulkhead. See, I moved it right there. So the parachute will be tied here, and then this part of the rocket will slide off the bottom part in this particular example.
Okay.
Okay. Now I need to put an egg in here, and the way I put an egg is I take this mass component, which is just they don't have. We'll call this a payload. And I don't know, I forgot how much the egg is, maybe 70 grams. And if I wanted to make it look a little like an egg, and you would have to have some packing material around it, obviously,
Okay.
foam or whatever. So now I put an egg in there. Okay.
Okay.
Okay. Now here's all right, let me put the parachute in, and then the other stuff, and then we'll talk about getting things. So let's say I put a parachute in here. Let's say I'm putting in, I don't know, 24-inch parachute. 24-inch. You buy a parachute, 0.8, this is something 0.8 is sort of average, unless you're getting a fancy parachute. Let's say it's nylon, 6 lines, and let's say it's really, the lines are 24 inches long. Whatever, you would put in whatever your real parachute is here.
Okay.
And you have to figure out what, let's say it's elastic cord, it's not 2 millimeters, maybe it's 12 millimeters. And now I can move the parachute around. Let's say the parachute's going to sit around here. And then, let's say it's in a pack like that. I'm just, and this says when the ejection charge goes off, the parachute deploys, which is what you want. The other possibilities are at apogee, but this is when you have electronics. So the only example you're going to have here is first ejection charge. And now we're also going to put in the shock cord. For torque, I would try to stay away from the elastic stuff that you have for Estes.
Okay.
It will melt. And typically you want your cord to be maybe 4 times the length of your rocket. So this rocket's a little less than 3 feet, so maybe you want 10 feet of cord. And let's pick something. A lot of people use thin Kevlar that you can get. But for kicks, we'll pick this. Now, why the length of that cord matters. Picture the rocket at apogee. You have the ejection charge come off, right? When you want the cord long enough to dissipate enough of that energy before it hits against each other.
Mm-hmm.
Of course, that shock, because that could be very severe.
So you said that was about approximately 4 times the length of the rocket?
Yeah, at least 4 times. Yeah,
okay.
And especially for small rockets. I mean, this rocket used a shock cord that's 25 feet long.
Wow. Wow.
Now this one was about a little over 5.5 feet when it was complete.
Wow. Okay.
But there's another belief that the shock cord should be a little taller than the tallest tree.
I guess when it's up in the air, it doesn't seem to, but like once it's on the floor, it seems to be a tangled mess being that long. But I guess,
No, it really isn't. All right. Now we're going to have hot gases coming out of here, so we need something to protect this, either wadding or there's Nomex pieces of cloth that people put around here. Regardless, we're just going to put a little mass here to represent something.
Got it.
Okay, so this is another mass piece. Let's just say it's 30 grams of something. And we're going to put that right there. Okay. All right. Not bad. Now, something that is obvious right now is this rocket when I put an engine in here, I'm going to move the center of gravity back so it's not going to be stable.
Right.
Which means I need to move the center of pressure back, which means I need to increase the size of the fins.
Yep. Got it.
All right, so I'm going to go back to the fins, and let's say I increase this by, oh, wait, I'm still in fin tabs. Go back. Record. Say I make the height 1 more inch. And see, now I've gone to 2 inches, maybe 3 inches. Okay, now I moved it. See how the center of pressure moved back, going from a 1 inch fin to a 3 inch fin.
Got it.
Now it's all the way back here. Okay. All right. I'm just going to save this as you're doing this as I'm doing, so you have a copy.
Yeah, but I'm not.
I could send you this copy too.
Yeah, but I'm not. Yeah, I'm following the steps, but I'm not fine tuning it like down to the numbers sometimes.
Okay.
I'm just kind of placing it in there. Yeah.
All right. By the way, I can look at this from the back, and this is what this rocket looks like now.
Oh, view type. Got it.
Right, 3 fins. Here's the centering ring. Okay.
Nice, fun. I like the 3D figure.
Yeah.
Cool.
Okay. Now, all right. This is 372 grams. This is well below what the total weight of a Tark rocket here. So now let's go to motors. Let's just fly this thing and see what happens.
Okay.
Oh, no motor mounts defined. So I want. Hold on. It's complaining. We go back to rocket. It's like where are you going to stick the motor? Motor. Okay.
And you just have to let it know that that's going to be the motor mount?
Yeah.
So it basically just wants to know which body tube you're going to put it into?
I think so. It's either that or it wants to know the inner thing. And I'm not exactly sure.
Okay.
Inner tube. Maybe that's what it wants. We'll just call that the motor mount.
Okay, so not the body tube, but the inner tube. Got it?
I think so.
Got it.
This tells you how often I do something from scratch.
Right.
Okay, there we go. All right. So now I go to motors. And I'm going to click new configuration. I'm going to select a motor. All right. And as a rule, you have to decide whether you're going to use Aerotech motors or Cicerone motors. But those are the 2 types. I'm just going to click Aerotech for now. And I'm going to go to F as the impulse because I think that is typical for Tark. And I know this is a 24 millimeter motor. And here they are. And you see some of these are single use. Some of these and some of these are reloadable.
I see. So it might be my preference setting, but my motor's dimensions are in inches here.
Yeah, it's probably it's just in it you have a preference set somewhere for inches.
Okay.
Okay.
Got it.
Now, a word on motors. So the single-use motors are what they are typically 25 5% more expensive than reloadable motors. A reloadable motor goes into a case. Hold on.
Interesting.
Let me show you. This is a 38 millimeter one, so yours will be smaller. But this is a case.
Mm-hmm.
This is metal. These, the fuel goes in here. You have to put in O-rings. There's a bit of a little process of putting one of these together. Okay, so the difference will be you have to buy these cases, and these, a 24 millimeter case may be, I don't know, 30, $40 for the case, and then the reloads are maybe $20.
Oh.
Or the or the single use ones maybe are $25.
Right.
Okay. Obviously, the single use ones are easier to start with, but a little more expensive. When you are in I'll say a more competitive mode, you'll use the reloadable ones.
I see.
And the reason is this, and now I'm sort of like 16 hurdles from where you guys are.
Mm-hmm.
But the commercial engines like this Aerotech engine, the fuel mass can vary by up to 10%.
Right.
Okay. Which means if you're trying to hit 800 feet, you can have everything the same and have one go to 880, and one go to 800, or one go to 750, just based on variation in the motor.
Right.
Okay. So what teams do is they'll buy, they'll try to get all their motors from a particular lot. They'll call up a manufacturer or the provider and say, I want everything that's manufactured on the same day to limit variability.
Wow. Mm-hmm.
And they will weigh each grain of the grains are like this big of the fuel, and mix and match between motors so that all the weight of propellant in each motor is approximately the same. So they account for the variability.
Right.
Probably something that you're not going to concern yourself with right away.
Right.
But in full disclosure, that's another reason why people go with the reloadables. The reloadables have whoever is reloading them, the team member who's doing that, if they mess up, the rocket blows up or has a failure, usually a catastrophic. It's becomes a very something that requires a little fire extinguisher at the pad usually. Okay, so there's a safety factor in there, but there's lots of middle school teams that use reloadable motors and learn how to do it. It's like 5 or 6 steps of putting it on and making sure the O-ring goes here and this goes there and it goes together. There's like 6 or 7 pieces to it to put it into that metal case. Okay. Well, let's pick and then this total impulse here is the newtons.
Okay.
Okay. And remember, you were dealing with newtons that were like 4 or 6.
Yeah.
So this is order of magnitude now. So let's just take this F-21. Okay. And these motors have variable times for their ejection charge. Okay.
Okay,
You
so
can buy
okay.
them, um, um, and teams have tools to actually, if they needed a 5, they drill into a 6 and make it a 5. But again, it's a level of fine tuning
Yeah, that's quite
that.
advanced. Got it.
I'm just sort of giving you an idea where. So let's just say I don't know what this is going to be. So I'm just going to pick a 6.
Yep.
Okay.
Okay.
All right. So now it's put the motor in here. You see, it shows you how far the motor goes up the tube.
Yes.
Okay. And it's sitting in there. Um, and now I go to flight simulations, and it shows me that this motor will, on this rocket, will go to 1,176 feet. I picked a pretty good delay. It says the optimal was 5.86. I picked 6.
Nice.
That's purely coincidental, by the way. It will go 203 miles an hour. G-force is 8 Gs off the pad. Flight time here is 74 seconds. So you look at this and say, okay, from a torque perspective, if I'm trying to hit 800, this is too high, and I'm way over on my flight time, right? Because I need a 42-second here,
Mm.
right?
So I'm sorry, Steve. So on the simulation, do you have to click on simulate and plot for you to get these results? Because mine's coming up blank.
Okay, so I put in the motor,
Yep.
right?
Yep.
And then I just clicked on flight simulations. And you could click on the simulation and then say run simulations.
Oh, okay. Maybe that's what it is.
Try that.
Okay, now I got the numbers. Okay, got it. It's plotting now.
All right, so your numbers, if your weight's a little off, maybe a little off from mine, but you'll see. Okay.
Okay.
Now, and by the way, if I go to plot, I just say plot, you'll see the flight.
Mm.
And obviously, this is the parachute coming down, and it goes up, and this is accelerated. Yeah, it's sort of a cool thing just to see.
Yeah.
Okay. All right. So, as an example of how I would adjust this, all right. So I need to go. I need less, no less than an F-21 off the pad because this is going too high, or I need to add weight.
Okay.
Okay, to the rocket. I could do either.
So I could pick a lighter engine or just add weight, you're saying.
Right. I could add weight.
Okay.
Okay. I have a good stability. I have a pretty healthy stability margin.
Mm-hmm.
If I add too much weight in the nose cone, I may become overstable. So my first inclination would be to go back here, select another motor. That was 56 newtons. Well, let me try this one. Except I don't need 8 seconds. Let's go back. That'll be too much. Oops. F44 at 4 seconds.
And as much as I'm enjoying this, I just want to be mindful of your time and respect it. It's 3:15, so
Well, let's do a couple more minutes.
sure,
Okay?
sure. I will not stop you, Steven.
Okay, so I have an F44
Got it.
at 8 seconds and one at 4 seconds.
Got it.
and I do flight simulations. Ah, okay. So now I'm at 872 feet. I'm getting much better, right? The optimal delay was 6 seconds, so and 54. So I'm getting better here. So if I want to adjust this one, let's go back to motors. I click on that. Select motor. Why is this not? There we go. Let's see, I want to go to 6.
Oh, okay. You have to click on the second column. Got it.
I'll put in 6 for 10. Let's go 6. The flight simulation. All right. So now I'm within 75 feet. And I'm within 13 seconds. I'm pretty good now. This motor is not bad for what I need for this rocket. If I want to get to 800 now, I might add a little weight, and I have some, place here. So let's just say I go back to my rocket design. I'll just show you one thing, but this is the kind of thing that then people start playing with.
Mm-hmm. So let me ask you from a practicality point of view, is it adding dead weight seems to be a waste to me, but is that not the way to think?
No, it's not, because you're only going to get so close with the motor and your design.
I see.
Right. The next level of calibration is adding some weight.
Got it.
Okay. And in the actual competition, when you guys win,
Yeah.
by the way, I've told you, middle school, I think 2 years ago, the middle school won. Same age kids that you have.
Really?
So, yeah.
Did you bring them to nationals?
No, not me. That wasn't
Right.
that wasn't a team I had anything to do with. It just was a middle school team that won
At nationals?
at nationals. Yeah.
Oh, great. Fantastic. Okay.
So
So there's hope.
there is hope. Yeah. Um, um, yeah, I was telling my wife I was talking to. She runs the TARC team at Morristown. She goes, "Oh, middle school might do well. They have less distractions than high school kids." But at national, when you're flying a rocket there, the first flight will be at the same, let's say, 800 feet, and then if you get to the final 25, they'll say, okay, now you're going to fly your rocket to 850 feet.
Oh, yes.
Or
There's
750 feet.
Yeah, there's two or three. I remember that. Yep.
And the way they do it typically is adjusting dead weight.
Do they? Okay, that's good to know. That way, and maybe have another set of rockets in hand.
Maybe.
But you're saying that the rocket, the engines itself, are not fine-tuned to make a 50 feet differential.
Probably not. No.
And that's where the weight comes in. Got it.
Yeah. So let's just say I'm gonna throw some weight in here just as an example.
Okay.
Let's see. I'm gonna put in 75 grams. And I threw it in right there. Okay. Now I go back. And you see, now my rocket's only going to 733 feet.
Got it.
Okay, I put in too much weight. 75 grams was too much. So I go back.
What constitutes these weight? Are they just like little masses of, I don't know, lead?
What some people do is, like, let's say I'm have it at the nose cone.
Yeah.
I would have like a screw coming out the back of the nose cone.
Oh.
I'm just putting nuts on them.
Oh, okay, got it.
Yeah, just regular hex nuts.
Oh, fantastic.
Right. All right. So 75 was too much. I said, oh, maybe I need 50 grams. So I'm like there, 50 grams. Let me go back here and fly it. Okay, now I'm 783 feet and 48. I'm very close, right? I just need a little less weight.
Yep.
I'm probably exhausted the accuracy of the model at this point,
Oh, wow. Okay.
but okay, let's say of course the egg may vary, so let me just make it a little less weight. I'll just take 5 grams off. 5 grams off. 791 feet. Okay, that's pretty good.
Mm-hmm.
That's curve 9. You know, now the other thing just to look at here, my flight time. I need to get this to, I think, 42 seconds or 43 seconds. So
Mm-hmm.
this is too much. So
So
what
maybe reduce my parachute size?
exactly?
Got it.
Now the way you practically reduce it is you reef the parachute. You know what that is?
Put a hole in the middle?
No, no. Don't, you could cut a hole in the middle, but so the parachute has, the lines that come down off of the parachute.
Right.
If you put if you instead of letting the lines go for 2 feet, if you go up 6 inches and put some tape there,
Mm-hmm.
the parachute doesn't open up as much because now you've taken 6 inches away.
Oh, I see.
And so rather than um, cut holes in the parachute,
Right.
then you can reef it
Got it.
and you can easily adjust it.
Got it.
Okay,
Got it.
but I don't think there's a way to reef it in the design. Let me see.
Maybe from the cord lengths, right?
Yeah, so cord length. So instead of 24-inch, let's see if we can reef this at reef it halfway to 12-inch. I've never tried doing that. Now you're in new territory for me. No, that didn't help. Um, so what I would do on this parachute, let's put it back to 24 inches. Whoops. Is say, all right, I'm not going to use a 24-inch parachute. I'm going to use an 18-inch parachute. And now I have 800 feet and 40.1 seconds. You do that twice, you go into the nationals.
Nice. That is fantastic.
And so that's how you would fly these online like this.
Got it. Let me ask you something. The G's, do I need to be mindful of that before I crack an egg while it's in flight?
Yeah. You're going to wind up with this kind of rocket. You're going to wind up with something around these G's. You're not going to get much less.
I see.
Okay. I think in this
Bless you.
rocket, which is only 456 grams, you have another 100 grams or 120 grams from a torque standpoint that you could play with. So you could make this rocket longer. You can make it heavier. It would reduce the G-force a little bit.
Mm-hmm.
But the other thing to know here, if I go to File up here, and you see this Print Export PDF. Do you have something like that? I'm just going to preview it. And it will print out. So this is the rocket we made. And it has a couple of different engines here. This one is 802 feet.
Nice.
Flight time, right?
Nice.
Burn time. Here's my remember we talked about thrust to weight ratio. This rocket is hauling the mail at 12 to 1. Yeah, here's another, one with a. The reason this is going earlier is the ejection charge is going off before it gets to apogee.
Mm-hmm.
And here it lists out every component and the mass of every component.
Mm-hmm.
So you can print this out, and when they design it online and compare it to the actual. And they have these actual diagrams of the parts
Oh,
that
nice.
we used. So look, the reality is a lot of these parts you're going to buy probably from Apogee Rocketry, which I think is one of the best for TARC parts. And they will have the nose cones and um, the pre-cut body tubes and these centering rings, and all the parts you'll be able to get off of them.
Okay. Let me
But
see file X.
well, that's the first time I've designed a rocket from scratch in a very long time.
And you hit the 800 mark on your second or third try.
Yeah. Well, and so you would build this rocket to this spec, and you would find out that hey, it's only going 730 feet. Okay.
Right.
But you're looking at this and saying, gee, all the weights are the same,
Yep.
everything's. I'm only going to. If that happens, there are two things you can do.
Back to calibration. Yeah.
In the calibration, you see where it says regular paint?
Yes.
And the kids will paint their rocket.
Right.
But if the rocket is going not as high as I think it is, I move this up.
I see. You try to make it rougher, so it'll simulate a rougher projection, right?
Right. And that's one level of adjustment. The
Right.
other level, and now we're into in the flight simulation. So I go to edit simulation. Hello.
Okay.
Why didn't that pop up? I think my openrocket might have just crashed. Well, that may be telling me it's time to flight simulate. I should be able to. Well, normally, if you edit simulations, you get another window here that tells you what the weather is outside.
I see it. Yeah, I see it. Average wind speed, turbulence, wind direction.
Right. And you could start adjusting those things. But like I said, if you build something and you're within 20 feet and within 5 seconds, you're already jumping for joy.
Wow. Yeah.
Right. But like I said, in the simulation, obviously you can get it very close, and then it's a matter of building. And then, rocketry is an art and a science. I mean, this is the science part.
Mm-hmm.
But the art part is being able to build it to spec. You build it repeatable. And but that's Open Rocket.
That's fantastic. I think I feel much more comfortable with it. That's for sure.
I mean, try. What you could do is just try building. Even a very simple thing from scratch, and putting in some some motors. I think this year's TARC design is simpler than in the past.
Mm-hmm.
I think 2 years ago they had 3 eggs. Sometimes they have a transition where they have like a 3-inch section here and then a 2-inch section up here. And there's a transition piece in the design to do that.
Yeah, I saw that.
Oh, one thing we didn't put on here. Um, for a Tark rocket, you're not going to use the launch log that you used for
On the SDs, okay.
you're going to use something called rail buttons.
I've seen those, yeah.
You seen them?
Yeah.
And so one rail button you'll probably stick down here, and another one like here.
Okay.
And obviously you put them right between two
The
fins
fins.
because there's going to be a rail that these
Right.
are going to slide into. The
Got it.
rail is a big aluminum rail. It's much sturdier than a rod. So
Yeah. Wobble.
well, the important thing for the rail buttons is to get them straight in line
Yep.
with each other.
Yep.
The way to do that is with a L iron,
Yeah, the steel angles.
steel angle, right?
Right.
Because you put a steel angle on a round body, it will be able to draw a straight line.
Right.
For those who don't have a straight do that, they use a door jamb.
Oh, that's, yeah. Okay.
Right? Yeah, so you just draw a straight line, and you put one rail button sort of close to the center of gravity. It doesn't have to be right at the center of gravity. I mean something lower down, and you know, then you'll just launch it directly from rails. Most clubs won't even let you launch an F off of a rod.
Yeah. Cool.
All right.
I think this is a lot to chew, and I'm going to start playing with it.
Yeah, look, I'm sure you'll have questions of this or that. Like I said, I'll send you a copy of the video so you can say, what did he say? But I just wanted to show you how to dial it in. So
Yep.
with a simulation and a particular goal of a flight time and a apogee. And by the way, for some reason, I think they have a randomizer factor in here. If I run this simulation 3 or 4 times, I may get slightly different.
Yeah, I've noticed that too. Yeah.
But it's important for the kids to keep very good records of every flight.
Right.
And the records include the wind, the temperature, which of the 4 rockets or how many rockets they build they're flying, and record keeping is key here. Fundraising is key.
Yeah.
I know my wife's team, which they haven't been in school, but normally they're selling Skittles.
Yeah.
I think they're sponsored by the local dentist or something.
Fundraising is a story of our lives.
Yeah, I mean, to run it, look, you can only do what you can do, and I'll say a high school Tark team that is has a chance at the final 100 will probably have a budget of between $2,000, $2,500, maybe.
Okay.
Some more, some less, but I mean it's well, the biggest expense you'll have are the motors.
Right.
And how many flights you're going to have. The building the rockets are relatively. I mean, they're more expensive than an Estes rocket to build, but they're
So I'm jumping ahead, but when it comes to procuring most of these parts, you're saying get them from Apogee. Are they mostly cardboard tubes, or do they come?
Yeah. You're gonna the body tubes are all going to be cardboard tubes.
Okay.
This is going to be some sort of wooden fin.
Yep.
The center rings are wood.
Okay.
Bulkheads are wood.
So typically when teams make, when we say they make these things, are they procuring different parts and assembling them together?
Yes.
Okay.
Yeah.
But they're not necessarily 3D printing, fins or
Some teams are now starting to do that.
okay,
Um, with some pretty successful, some not.
right,
There's a learning curve to it.
yeah,
There was a team from Summit High School that was making a complete 3D printed rocket.
wow,
Like everything was 3D except I don't know, almost everything, and it looked good. It they had I don't know whether their problems were with the 3D printing or other engineering factors,
right,
but it didn't work out well for them.
right,
I know other teams have 3D printed the fins,
right,
and some even tried to 3D print sort of an egg holder thingy.
right,
Although this is normally you get some foam and you carve out the foam and you
right.
figure out how to do that. So that's not that expensive. But yeah, I mean, uh, if you have a 3D printer and want to make the fins, go for it and try
Yeah,
it out. Um, the the other thing that can affect um, height is the fins. Normally, if they're just cut, we'll just have like a square top.
right. To try
Right?
to make it more aerodynamic, you taper it.
If you taper it, that's a big impact.
Wow. Okay.
Uh,
I've seen magazine articles that gets into that.
yeah, it's I had in fact I never realized it, but I literally just last year I have this rocket that's I don't know, it's about an 11-foot missile design, looks like a missile, and every time I launched it compared to Open Rocket, it was off by like 30%. I'm like,
Wow.
and I'm like, and all my other things in my fleet were pretty close.
Yeah.
Why is this one always off by? I mean, and and, and part of it is it's susceptible to wind. It's a little overstable because it has 3 sets of fins on it and a bunch of things. And and finally I realized, oh, all these fins, there's so many fins on it, are tapered,
Mm.
and they're really sharp. They're really tapered well.
Mm-hmm.
From the guy I got it from, and I changed that, and then the Open Rocket thing was right on.
Oh, wow.
So I mean, this was like, I mean, these were going like 7,000 feet, and they'd be off by 600 or 700 feet consistently, and I was like, or sometimes off by 1,000 feet. I'm like, how is this possible? And
Right.
and once I hit the tapered fin part on Open Rocket, it was very close. So there's
Interesting.
that's another variable of fine tuning. Or if you're going to taper them to begin with, fine, and then you have other things to fine tune. So it's um, um, choice. But these rockets probably are $30 to build from
Mm-hmm.
all the parts. I don't know. Um, Maybe a little bit more with the parachute or whatever. I mean, relatively speaking, that's not where you're going to spend a lot of the money.
Right.
The altimeters are 30-40 bucks each.
Right.
Um, as long as you're not blowing up your rockets, you're not blowing up your altimeters.
Right.
Uh, but you're going to wind up with a few of those. It depends what kind of tools you got at the school. Um, Glue. Um, a lot of schools use the West system, pump glue, pump
Mm-hmm.
epoxy. That's really good for model rockets. Um, um, the glue guns are very, very bad. And
They're too heavy, right?
no, the glue gun,
Yeah.
it'll melt. Your rocket
Oh,
will
I
just
see.
it'll fall apart.
I see.
It'll look good on the shelf, and that's about it. Um, you can use wood glue, obviously, on all of this because it's all wood and cardboard.
How about crazy glue?
Um, Crazy Glue has certain um, applications, but not as a general, because it's not good in shear, I believe.
Oh, I
So,
see.
for example, when you're putting this fin through the tab,
Yep.
you have seven. You're going to wind up with 7 attachment points, because here's one that's the root, which is against the tube.
Yeah.
And then you're going to put what's called a fillet on either side. And you could put a fillet on the bottom, and then you're definitely going to put fillets on the top. What's a fillet? A fillet is a little dab of glue that sort of goes along this line here.
Yep.
Normally, you stick your finger and 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 it adds a lot of strength. Now, if you can't get it inside here, you know, don't worry about it. Before you, um, what a lot of people do is this bottom um, uh, centering ring is left loose, so they put it in. This centering ring gets glued in
Mm-hmm.
with the tube. It's made that it's all straight with this ring here, but this ring's not glued in. It's just sort of fit in. You
Mm-hmm.
take it, right, and then you put the fins in. Now, once the fins are in and this is in, you take this out, and you have access inside the tube to add some glue here and here and here.
I see. Yeah.
And then you can put this bottom ring back on.
Right.
No charge for that hint. But wood, the good, not white glue, the carpenter's glue.
Right.
The white glue again is just terrible for rockets.
Right.
For the high, for SDs it's okay, but for anything with this, this is an order of magnitude more power than those SDs rockets, and you don't want white glue on that.
Got it.
Um, but yeah, it's all going to be cardboard. This is going to be plastic, and a few wood parts. And like I said, look up some things for motor retention.
Mm-hmm.
Motor retention is so when the ejection charge goes off, the motor doesn't go out the back.
Right.
And the other thing that you should realize is that the kids are probably going to put in the top of this motor, depending upon the manufacturer, whether it's reloadable, some have the black powder charge already put in here.
Mm-hmm.
Sometimes they give the black powder in a little vial,
Mm-hmm.
and the Rocketeer puts it in.
Oh, I see.
I would just say be very respectful of the black powder. It doesn't, it doesn't normally just go off on its own, but it has a good healthy wallop if it does. So
Wow.
Because it's the charge that's going to separate this rocket. So I've known adult Rocketeers who've done stupid stuff